NENOMATICA, where mathematics meets YouTube excellence. Example, we will form a new quadratic equation whose roots are the negatives of the roots of a given quadratic. Suppose the original quadratic is ax squared plus bx plus c equals 0. Our goal is to follow the exact substitution method to get the new equation. According to the rule shown in the reference, if we want the second quadratic whose roots are the negatives of the original roots, it is enough to replace b by negative b. So the new quadratic becomes a y squared minus by plus c equals 0. Now, we justify the rule step by step using substitution, exactly as shown in the method. Let y equal negative x, which means x equals negative y. Substitute x equals negative y into the original equation. We get a times negative y squared plus b times negative y plus c equals 0. Simplifying gives a y squared minus by plus c equals 0. This matches the rule. For intuition, in this lesson, we will form a new quadratic equation whose roots are the reciprocals of the roots of a given quadratic. First, here is the problem statement. We start from the standard quadratic equation, ax squared plus bx plus c equals 0. To make the reciprocals appear naturally, let y equal 1 over x. Then x equals 1 over y. We will substitute this expression for x into the original equation. To visualize the substitution, notice the curve y equals 1 over x on a small set of axes. Now substitute x equals 1 over y into ax squared plus bx plus c equals 0. That gives a times 1 over y squared plus b times 1 over y plus c equals 0. Next, multiply the entire equation by y squared to clear denominators. We obtain a plus by plus c, y squared equals 0. Finally, rewrite in standard descending powers of y. cy squared plus b, y plus a equals 0. A quick justification. If our 1 and our 2 are the roots of the original equation, then x equals our makes ax squared plus bx plus c equals 0. With y equals 1 over x, the new roots are 1 over r1 and 1 over r2. Notice how the coefficients a and c swap roles in the new equation. Let us cement the idea with a quick check. Suppose 2x squared minus 5x plus 3 equals 0. The reciprocal equation should be 3y squared minus 5, y plus 2 equals 0. In this video, we will prove a beautiful symmetry between two quadratic equations. We will show that the solutions of ax squared plus bx plus c equals 0 and cx squared plus bx plus a equals 0 are reciprocals of each other. Here are the two equations side by side, sharing the same middle coefficient b. Both equations have the same discriminant, delta equals b squared minus 4ac. This will be the key. Let the roots of the first equation be x prime and x double prime. By the quadratic formula, x prime equals negative b plus square root of delta over 2a, and x double prime equals negative b minus square root of delta over 2a. Let the roots of the second equation be x1 and x2. Using the same delta, we have x1 equals negative b plus square root of delta over 2c, and x2 equals negative b minus square root of delta over 2c. Now we multiply x prime and x1. Watch how the difference of squares appears. Multiply the numerators using negative b plus root delta times negative b minus root delta, which equals b squared minus delta. The denominator is 4ac. Substitute delta equals b squared minus 4ac. Then b squared minus delta becomes b squared minus parentheses, b squared minus 4ac parentheses, which simplifies to 4ac. Since the product is 1, x prime equals 1 over x1. They are reciprocals. The exact same algebra shows that x double prime times x2 equals 1. Therefore, x double prime equals 1 over x2. Conclusion. For the pair of quadratics ax squared plus bx plus c equals 0 and cx squared plus bx plus a equals 0, the roots are paired as reciprocals. Example. Problem statement. Form a new quadratic equation whose roots are n times the roots of the original quadratic. Ax squared plus bx plus c equals 0. We will keep the on-screen math bold and clear and follow a precise three-step structure. Step 1. The rule. When each root is multiplied by n, the new quadratic in the variable y is a y squared plus b and y plus c and squared equals 0. We will prove this next. Step 2. Proof. The roots of the new quadratic are y, and each is n times a root x of the original. So y equals nx, which implies x equals 1 over n times y. Start from the original equation, a x squared plus bx plus c equals 0. Substitute x equals y over n into it. This gives a times parenthesis, y over n end parenthesis squared, plus b times parenthesis, y over n end parenthesis, plus c equals 0, which simplifies to a y squared over n squared plus by over n plus c equals 0. Now multiply the whole equation by n squared to clear denominators. We obtain a y squared plus b and y plus c and squared equals 0, which matches the rule. Step 3. Result and recap. The new quadratic whose roots are n times the original roots is a y squared plus b and y plus c and squared equals 0. Recipe. Replace x by y over n, simplify, and clear denominators by n squared. And that completes the step-by-step construction of a new quadratic equation when all roots are scaled by n. Example. Solve the quadratic by following the exact algorithm shown. Remove the coefficient of x squared. Factor, then divide the roots by that coefficient. Our problem is 7x squared minus 16x plus 4 equals 0. Step 1. Remove the coefficient of x squared by dividing the entire equation and multiply that coefficient into the constant term. That gives x squared minus 16x plus open parenthesis 4 times 7 close parenthesis equals 0. Now multiply to simplify the constant x squared minus 16x plus 28 equals 0. Step 2. Factor the new monic quadratic. We need two numbers that multiply to 28 and add to negative 16. Those are negative 14 and negative 2. So it factors as open parenthesis x minus 14 close parenthesis times open parenthesis x minus 2 close parenthesis equals 0. Step 3. Set each factor equal to 0. So x minus 14 equals 0 or x minus 2 equals 0, giving x equals 14 and x equals 2. These are the roots of the transformed equation. Step 4. To get the solutions of the original equation, divide each root by 7, the original coefficient of x squared. That gives x equals 14 over 7, which is 2, and x equals 2 over 7. Therefore, the solutions to 7x squared minus 16x plus 4 equals 0 are x equals 2, and x equals 2 over 7. I will highlight both on a number line to build intuition. In this example, we will solve the quadratic equation using the forming a new quadratic method. Here is the example we will solve. Step 1. Remove the coefficient of x squared and multiply the constant term by that coefficient. The coefficient equals 4. We create the related monic equation x squared minus 7x plus negative 15 times 4 equals 0. Write that exactly as x squared minus 7x plus open bracket negative 15 times 4 close bracket equals 0. Then simplify the constant. Step 2. Factor the new quadratic. We need two numbers that multiply to negative 60 and add to negative 7. They are negative 12 and positive 5. So the factorization is open parenthesis x minus 12 close parenthesis times open parenthesis x plus 5 close parenthesis equals 0. Step 3. Set each factor to 0. The solutions of the new quadratic are x equals 12 and x equals negative 5. Step 4. Convert back to the original equation. Because we multiplied the constant by a and made the equation monic, the original roots are each new root divided by a. Here it equals 4. So x equals 12 over 4, which is 3, and x equals negative 5 over 4. Recap. We formed a new monic quadratic by multiplying the constant by a. We factored it, solved for the temporary roots 12 and negative 5, and then divided both by 4 to get the solutions 3 and negative 5/4. In this example, we will form a new quadratic equation when every root of a given quadratic is increased by m units. We start with the original equation in standard form. Then we describe the new root relation, and finally we substitute, expand, and simplify to obtain the final formula. Let y denote a new root. Each new root is m units greater than an old root, so y equals m plus x. Therefore, x equals y minus m. Now substitute x equals y minus m into the original equation. We get a times y minus m quantity squared, plus b times y minus m plus c equals 0. First expand the square and distribute. Y minus m quantity squared equals y squared minus 2m y plus m squared. Multiplying by gives a y squared minus 2 a m y plus am squared. Next expand b times y minus m to get plus b y minus bm. Combine all terms with plus c equals 0. Group like terms to write the result as a quadratic in y. The y squared term is a y squared. The y term is b minus 2am times y. The constant term is am squared minus bm plus c. So the new equation in y is a y squared plus b minus 2am times y plus am squared minus bm plus c equals 0. Let's verify with a quick numeric example for intuition. Suppose it equals 1, b equals -3, c equals -10, and m equals 2. The formula predicts the new equation, y squared plus open parenthesis -3 minus 4 close parenthesis, y plus 4 plus 6 minus 10 equals 0. That simplifies to y squared minus 7y equals 0, or y times y minus 7 equals 0, so the new roots are 0 and 7. The original equation x squared minus 3x minus 10 equals 0 has roots 5 and -2. Adding m equals 2 to each gives 7 and 0, which perfectly matches our new equation. Therefore, when each root of x squared plus bx plus c equals 0 is increased by m, the new quadratic equation in y is as follows. In this lesson, we will solve a classic algebra problem using the shifted roots method. Our goal is to compute the greatest integer of ab over 4. We'll begin by carefully writing the given system and the target. Step 1. Let alpha and beta be the roots of the first quadratic. Then, by the sum and product of roots for ax squared plus bx plus c, we have alpha plus beta equals over 2 and alpha beta equals b over 2. Step 2. The second quadratic has roots shifted by 1/2, alpha minus 1/2 and beta minus 1/2. For 2ax squared plus ax minus 6 equals 0, the sum of roots equals -1/2. Therefore, alpha plus beta minus 1 equals -1/2, so alpha plus beta equals 1/2. From alpha plus beta equals over 2, we immediately get it equals 1. Step 3. Use the product of the shifted roots. For the second quadratic, the product equals -3 over a. So, left parenthesis alpha minus 1/2 right parenthesis times left parenthesis beta minus 1/2 right parenthesis equals -3 over a. Expanding gives alpha beta minus 1/2 times alpha plus beta plus 1/4 equals -3 over a. Substitute alpha beta equals b over 2, alpha plus beta equals 1/2, and it equals 1. We obtain b over 2 equals -3, hence b equals -6. Step 4. Compute the target greatest integer of ab over 4. With it equals 1 and b equals -6, ab over 4 equals -6 over 4 equals -1.5. Therefore, the greatest integer, less than or equal to that, is -2. Recap. We used sums and products of roots, recognized a shift by 1/2 in the second quadratic, solved for it equals 1 and b equals -6, and then took the floor of ab over 4 to get -2. That's the solution. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.